In this video, we're going to talk a little bit about how radiation is detected and used in different ways. In the Canvas site, I have already posted a number of videos on this from external sources, and I strongly encourage you to watch those for the details. They are very well produced and give you a lot more information. Nuclear chemistry is not my strong point necessarily, so those videos are going to give you a lot more information and detail than I will give you here, but we'll do a quick rundown. So the two different types of detection that we'll briefly talk about are film badges and Geiger counters. So film badges are typically worn externally somehow, clipped to a lapel or in a pocket, and these have a film inside of them that, as they are exposed to certain radiation, will change color, a lot like an X-ray film will, so that you can then monitor how much exposure you've had to that particular radiation. So if you work in a field where you are frequently exposed or there's known exposure possibilities, those are worn to detect how much radiation you've been exposed to. At some point you might reach a point where you've been exposed to too much and you need to stop that particular job. A Geiger counter is an instrument that's used to detect radiation. You might have seen these on TV or something. They kind of make that beeping or clicking sound whenever it comes across something that's radioactive. What's happening is inside that Geiger counter there's gas molecules, and there's a window that your radiation can pass through, and if that radiation reacts with those gas molecules, it then produces electrons. Electrons then cause electricity to flow. If that electricity is flowing, then your detector gets the energy and creates the sound. If there is no radioactive substance present, there are no electrons, and therefore you don't get the detection. For anything that is exposed to radiation, whether it's alpha, beta, or gamma radiation, there's a different level of penetrating ability and ability to actually cause damage. So this particular diagram gives us a good idea of what those different levels are. So you can have exposure to any three, right? So here's our radioactive source that's actually giving off radiation. And in this example, it's in a lead box that totally blocks radiation, except for a little gap where we're letting out a little bit. So if we put a piece of paper in this stream of radiation, it will block the alpha. Okay, so it doesn't take much much substance at all to block alpha particles. Just a thick sheet of paper is enough. So the penetrating ability of alpha particles is very low. What does come through are beta and gamma rays. The 1 centimeter thick of aluminum is enough to stop beta particles. So beta particles have more penetrating ability than the alpha particles do, but still not incredibly significant because a 1 centimeter thick piece of aluminum is not a lot. If we go up to 5 centimeters of lead in concrete, we are able to stop some of the gamma rays, but not all of them. So that means the gamma rays have a very high level of penetrating ability. Okay? So alpha particles, low penetration, gamma particles, high, which is okay, right? Gamma radiation, if it gets into your body, is less harmful than alpha particles. Okay, so alpha particles, your skin is able to completely block alpha radiation. But if somehow those alpha particles get inside your body, like you ingest them somehow, they can cause significant damage. Beta particles, if they are in contact with your skin for a prolonged amount of time, it can cause burns on the skin. Beta particles as well, if they get inside your body, can create some significant damage. Okay, so there's a difference between the penetrating ability and the damage that it can cause. Again, the external videos will give you a lot more information on this. So quick check here. What type of radiation has a low penetrating ability but causes significant internal organ damage if you are able to, or if you happen to ingest that substance? And that would be the alpha particle. There are several different sources of radiation that you should be familiar with. One would be background radiation and the sources of that background radiation, and then radiation that is due to human activities. So here's the pie chart that breaks down some of the different pieces. So the yellow region here, all of these are natural sources, and we consider this to be background radiation. So these are things that you're going to come into contact frequently, usually not something that you can avoid. Um, in most cases, not something that you need to avoid in normal circumstances. Radiation seepage, though, is something that is concerning, right? If you've ever heard, sorry, not radiation, radon seepage, this is something that can happen within homes and is something that is monitored, because if you get a significant level of radon within your house, one, it's difficult to remove, and two, it can cause damage. So there are tests out there to test radon levels within the home. Some other examples that are listed here are then those produced by human tasks, so things like x-rays, nuclear medicine, consumer products, and others. So these would not be considered natural or background radiation, but instead human produced. But again, are things that you could be exposed to. So which of the following types of radiation is going to give the greatest background source? And that was the radon seepage. So those human-made sources, a lot of them were due to nuclear medicine. So we're going to talk briefly about the different things that radiation can be used for when it comes to either diagnostic or therapeutic uses. So a few things nuclear medicine is commonly used for. It can be used for things like locating infections, locating impaired muscles or impaired circulation. It can also be used to monitor thyroid activity and also for detecting tumors. You have probably heard of radiation therapy that's used to try to eliminate cancer. That is exposing the tumor to radiation in hopes that it kills it. So that's a form of nuclear medicine. A few things are always thought about before a radioactive nuclide is used on the body. So one, it needs to be detectable outside the body. So if you put it inside, you still have to be able to detect it from the outside. It needs to have a short half-life, so we don't want it to stick around for a long time. There needs to be some way that your body is able to eliminate that substance. And then it also needs to be compatible with your normal body chemistry. So you don't want it to be interfering with the reactions that your body needs to do to keep you alive.